This problem is related to the concept of standing waves in a string. And problem says, two uniform strings of mass per unit length mu and 4 mu and length L and 2L respectively are joined at point O and tied at two fixed ends P and Q as shown in the figure. So this is one string, this is length L and mass per unit length mu, and this is another string, length 2L and mass per unit length 4 mu. These are joined at point O and fixed at point P and Q. The strings are under tension, uniform tension T. So there is a tension throughout, and this is a uniform tension, that is T. If we define the frequency nu naught, and this is equals to 1 by 2L a square root T by mu, which of the following statements are correct? So 4 statements are given, and then we have to find which is correct and which is incorrect. Now the first option is with a node at O, and the second is with an antinode at O. Similarly here with an antinode at O and with a node at O. So this means we have to analyze this problem when there is a node at O in one situation and in another situation when there is an antinode at O. So let us analyze this. So if I have a node at O, this means the particle will not move, so there will be a minima. So the string will look something like this. So I will have some number of loops in this string and some number of loops in this string, so that the point O is a node. Let us say lambda 1 is the wavelength in this part of a string and lambda 2 is the wavelength in this string. Nu naught is given in the problem, that is this value. So this is the situation with node at O. Now if you remember, length of any loop in case of a standing wave is lambda by 2. So if I have n1 number of loops from here to here, then I will have length will be n1 times lambda 1 by 2, because the wavelength in this case is lambda 1, and this is also equals to L. So we can write this equation, that is L is equals to n1 times lambda 1 by 2. Similarly, I can write another equation from this string, that is n2 times lambda 2 by 2, and this should be equals to 2L. So this is the length 2L, and this will be equal to number of loops. Let us say number of loops is n2 and length of each loop, that is lambda 2 by 2. So you see, in such cases frequency will be same in both the wires while wavelength can be different. The frequency is same, but here I have a wavelength of lambda 1 and here I have a wavelength of lambda 2. Now let us analyze wire 1. We know that velocity in a wire is given by a square root tension divided by mass per unit length. So velocity is equals to a square root tension divided by mass per unit length mu, and velocity is also equals to nu times lambda. So let us say in this case frequency is nu 1 and wavelength is lambda 1, but I said frequency will be same in both wires. So let us say lambda 1 is equals to, basically nu 1 is equals to nu 2 and this is equals to nu. So nu 1 is equals to nu, and lambda 1 from this equation I can find. So this will be 2 times L divided by N is equals to lambda 1. So I can write 2L by N1. Similarly, I can write the same equation for wire 2. What will be the velocity? Under root tension divided by mass per unit length, but in this case mass per unit length is 4 mu. So tension divided by a square root. So this is a square root tension by 4 mu. And this is equals to frequency times wavelength. Let us say frequency is nu 2, which is basically equals to nu, and lambda 2 will be 2 times 2L, that is 4L by N2. So that is 4L by N2. Now if you take 4 outside, basically 2 will come outside. So this will be T by mu, and this 2 if you multiply, so this will be 8L by N2. So T by mu, a square root T by mu I know here, and a square root T by nu I know here. I can equate these two. So I can write 2L by N1 because this mu and this mu will cancel out. So 2L by N1, this is equals to 4L and times 2, that is 8L divided by N2. So from here I can write N2 by N1 is equals to 4 by 1. So minimum value of N1 is 1 and minimum value of N2 is 4. So I can say N1 equals to 1 and N2 equals to 4. This means in this wire I will have only one loop, and in this wire I will have 4 loops. Now we can also find corresponding velocity. So velocity is, let us say using the first wire, velocity is a square root T by mu, and this is equals to nu times lambda, and lambda in this case 2L by N1. So this formula I am using. So from here I can write nu is equals to, this N1 goes on the top and 2L will come in the denominator, and in this case minimum value of N1 is 1. So nu is equals to 1 by 2L, a square root T by mu. So this is equals to nu naught. So when I have node at O, the lowest frequency will be nu naught, because nu naught is same as this value nu. I can have higher frequency. If I take N1 equals to 2, I will have higher frequency, but the lowest frequency will be equal to nu naught. Now this situation is shown here. So in wire 1 I will have one loop, and in this case I will have 4 loops. So this is the modes of vibration. How many total number of nodes I have? 1, 2, 3, 4, 5, 6. So including this node and this node we have total of 6 nodes. So that was one option. Now let us analyze the problem when we have a empty node at this position O. So if I have an empty node at O, this means now particle will have maximum amplitude at this position. So I will have something like this from this string, and from this string this like this. So this will be lambda by 4 only, and this will be lambda by 4. So what I can write? This length is 2L, and this will be equals to, let us say we have N2 number of loops. So N2 times lambda 2 by 2 and 1 extra, that is half, that is lambda 2 by 4. So we can write 2L is equals to 2N2 plus 1 by 4 times lambda 2. Similarly I can write for this L. L will be now N1 times lambda 1 by 2, because I have N1 number of complete loop and 1 half loop. So this will be 2N1 plus 1 divided by 4 times lambda 1. Now I can write velocity in wire 1. Velocity is given by a square root T by mu, and this is equals to nu times lambda. Nu1 lambda 1, frequency will be same in both the wires. So let us say nu1 is equals to nu. What will be lambda 1? I can calculate lambda 1 from here. So this will be 4L divided by 2N1 plus 1. So that is this value. Similarly, I can write this expression for wire 2. So velocity is a square root tension divided by mass per unit length, that is 4 mu, and this is equals to nu times lambda, and frequency is same in both the wires. So this is nu, and lambda will be 4 times 2 8L divided by 2N2 plus 1. I can further take this 2 outside and multiply here. So I will have 16L. So this is a square root T by mu is equals to nu times 16L by 2N2 plus 1. Now this and this is basically equal. So I can equate this and this. So that is here. So if I equate these two, I can get this relation, that is 2N2 plus 1 divided by 2N1 plus 1 equals to 4. So this is an odd number and this is also an odd number. So odd number divided by the odd number cannot be an even number. So this is not possible. You can verify the options. So the first option is with node at O, the minimum frequency of vibration of the composite string is nu naught. This is what we have proved. With antinode at O, the minimum frequency of vibration of the composite string is 2 nu naught. So basically at antinode at O is not possible. So this option is incorrect. When the composite string vibrates at the minimum frequency with node at O, it has 6 nodes including the ends nodes. So this is correct. We have shown this. No vibrational modes with an antinode at O is possible for the composite string. So this is also correct. As I said, with antinode at O, there is no vibrational mode is possible. So I hope you enjoyed this problem, and if you like my videos, please share with your friends, like on my channel and subscribe to my channel. I will see you in the next video. Thank you.